So we have a power plant that has an electric generator. So right here is our generator. Okay, it's operating at steady state with an input shaft. So here is our input shaft. It has a rotating speed, they call it omega. A lot of times people will say N, but anyway, it's 1800 RPM, revolutions per minute. And the torque, tau, will be 16,000 Newton meter. All right. It also produces current over here, electricity. So you have the current, let's say I is a good symbol for current, 230 amps, and a voltage of 13,000 volts. I like to use E for electromotive force, maybe just EMF. Electromotive force is 13,000 volts. Okay. The rate of heat transfer between the generator and its surroundings is related to the surface temperature. So we'll think about having a temperature right here, TB. That's our surface temperature. And the lower ambient temperature, T0, far away, and is given by the equation Qdot. And I'll change this notation here, but it's like we're trying to predict the rate of heat transfer coming off of the generator to the surroundings, and the equation is Q dot. The rate of heat transfer is predicted by a coefficient. Well, it's a negative HA. Then we have TB minus T0. So they put the negative in there because the direction would be into the generator, but we know that the generator is going to be hot if it's running, not cold if it's running, and so the direction will actually be out into the surroundings. So I'm going to just get rid of that negative sign and take ownership. We know the direction of the heat transfer. Okay. They give you the value of H, the value of area, and the value of T0. So it's like we've got T0, A, and H known. We do not know Q dot. We do not know TB. Those are unknowns. So the first part is determine the temperature TB. How do we find that temperature TB? Right there. Well, if I take that this rate of heat transfer equation and I can solve for TB, TB will be T0 plus Q dot divided by HA. All right, now all I need to find is Q dot. Well, how do I find Q dot? We'll introduce a control volume, our system, which is just around the generator. And the boundary of our system corresponds with this TB, that temperature of the boundary of our system that's surrounding the generator. And we do a first law analysis. And so in an energy balance, all the ins must equal all the outs at steady state. And our inflow is by this shaft power. So W dot shaft coming in. How about an out? Well, W dot electric. We want as much of that shaft input power to be converted in the generator to electric power and come out. But then we're going to have some waste in this heat transfer to the surroundings. So we go back to first principles to calculate the power that's coming into the generator by that shaft. And it's the product of the rotational speed, omega, times the torque, tau. But this omega has to be in units of not revolutions per minute, but has to be in units of radian per second. So what do? We convert by having 1800 revolutions per minute, and each revolution is 2 pi radian, and each minute is 60 seconds. So our revolutions go and our minute goes, and we're left with radians per second, and we can make that calculation. Let me see if I did. It turns out to be 188.5 radian per second. What is radian? It's a length over length, so it's really dimensionless, but I know that I'm talking about an angle of rotation, a length over length, so that's radian. Okay, so we can make the calculation. What's that shaft power? 188.5 radians per second times the torque in the shaft, 16,000 Newton meter. And here we use that a Newton times a meter is a joule, then a joule per second is a watt, and we can calculate. And if you want to put a kilo, you just put it like a kilo divided by 1,000, and we can convert that to kilowatts. And we find that the power in the shaft is 30. Clean that up. Come on now. 3015.9. That's a 0. Come on. Kilowatts. Okay, now we need to do the same thing for the electric power going out. W dot ELEC, electric. Well, if I know there's no three-phase, so this is kind of simplistic, but no phase shift or anything like that. It's just the voltage times the current. So we'll just have the voltage of 230 amps times the current, not the current, the voltage of 13,000 volts, and the current in 230 amps, and then a watt is a amp volt. And this comes out to be, for the electric, 2990 kilowatts. All right, so we find that the Qdot is equal to the shaft power in, 3015.9, minus the electric out, 2990. Hence, the rate of heat transfer to the surroundings is 25.9 kilowatts. So we just were able to come up here and solve for Qdot. So we can go back to this equation right here. We have Qdot, we have H, we have A, we have T naught. And because I'm running out of space, I always am, I'm going to say that we're able to calculate that the boundary temperature. Now, you just have to be careful here. This T naught is given to us at 298. Leave these all. This is a temperature change in Kelvin. And then you calculate TB is 311.8 Kelvin. That's the answer for part A. Okay, for the generator is the system. That is our system. Okay, determine the rate of entropy production. Ooh, so how do we calculate the rate of entropy production? Well, we don't use the energy balance. We've already used that. We use an entropy balance, or second law. And that second law basically says that there's no, it's running at steady state, so no accumulation or depletion. We have a rate of heat transfer, and since it's leaving the system, I'm going to force a minus sign on that because we calculated it to be a positive 25.9. We divide by the boundary at which it's leaving the system in Kelvin, and that's going to be a entropy removal rate. All right, and then we don't have any other heat transfers, and the only other we have is the entropy generation rate. That's it. That's our second law. It boils down to something that's simple. So sigma dot is equal to Q dot divided by TB. And we already calculated 25.9 kilowatts. And our boundary temperature has to be in Kelvin, 311.8. And we find that sigma dot, the rate of entropy production, is equal to the 0.0832 kilowatts per Kelvin. That's the answer for part B. You could have, be careful, every now and then they'll say they want it in watts per Kelvin. If they wanted it in watts per Kelvin, then it would be 83.2 watts per Kelvin, but they didn't. Just watch your units. Now for part C, if the system boundary is located to take in enough of the nearby surroundings for the heat transfer to take place at a boundary temperature T0, basically an enlarged system. When you have an enlarged system, you think about taking it and going all the way out here like that. And so now the boundary temperature TB is equal to T0. Well, the heat has to continue to be transferred. Once it's going, steady state, it's going out and it's getting all the way out to the surroundings where it's at T0. But if you have a large control volume or large system, then TB way out here is T0. All right. So determine the rate of entropy production for that enlarged system. Well, the only thing that's changed is this temperature right here. That temperature isn't 311.8. It's where is it at? 298 right here. It's 298 Kelvin. And so when you rerun, you find that sigma dot is going to be a little larger, 0.0870 kilowatts per Kelvin. And then you say, why is that larger? Because in this space right in here, there's heat transfer from a higher temperature coming in to a lower temperature going out. If you just focused on a kind of this green hatched system, it would be, maybe I should try and draw it like this. And it's kind of just a system of air where the boundary over on this side is higher temperature. The boundary is lower temperature. You have a heat transfer through that system. Well, there's entropy generation there due to the irreversibilities of heat transfer. That's why it's a little larger. But anyway, that's the answer for part C.